This is Redox video 5. We're going to talk about voltaic cells. So this video and the next video fall under a branch of chemistry called electrochemistry. And what electrochemistry is going to look at is really the application of the redox reactions that we've been working on. So some redox reactions are going to occur spontaneously, just meaning on their own, and some are not going to occur on their own, so they're going to need some type of electricity to force a non-spontaneous reaction to happen. So just like a battery, an electrochemical cell is any device that produces electric current by a spontaneous redox reaction. So we're going to look at how this happens. Initially, this might look like a little bit overwhelming. Just take it in. On a piece of paper, I'd like you to draw the two cells. So we have two half cells. Just try your best to draw what's happening. And we will just go through a little explanation of what's happening. So inside this voltaic cell, it also has a couple other names, like on the SAT you might hear it called the Daniell cell or galvanic cell. But there are two electrodes. So on the left, we have zinc, and it doesn't matter, it doesn't have to be on the left-hand side, but just so that you see, this is the zinc electrode over here, and on the right-hand side, we have the copper electrode. One electrode is called the anode, and one electrode is called the cathode. We're going to use an acronym to try to help us remember what's going on at the anode and cathode. So we have an acronym ANOX. ANOX, I'm all about acronyms, you know that at this point. But ANOX stands for oxidation occurs at the anode, and we have red cat, reduction occurs at the cathode. So we know that oxidation is loss of electrons, so at the anode electrons are being lost, and at the cathode reduction is occurring, so at the cathode we're gaining electrons. To identify which electrode is the anode or cathode, we can use table J. So if you open up table J, remember yesterday we talked about the fact that if you're higher up on table J on the metal side, you're more likely to lose electrons and be oxidized. So the one that is higher up is going to represent the anode. Since zinc is higher up on table J, zinc will be the anode, and in this case copper will be the cathode. It's more likely to be reduced. Electrons will always travel from the anode to the cathode. So I say it's alphabetical, A to C. Electrons always go anode to cathode through the wire. So here you see these negative circles. That's just to indicate that the electrons are moving through the wire. Sometimes on a Regents question they call the wire the external circuit. So electrons go from the anode to the cathode through the external circuit or through the wire. We could actually see like a light bulb here because, what's happening is the electrons will be able to produce their recordable voltage. In this case, the electrons are able to conduct electricity to make that light bulb light up. We could also put a voltmeter there, and we could record how much voltage is produced when this reaction actually happens. Okay, if you notice in the middle, we have this white filter. This is called a salt bridge. Sometimes it will look like this. Sometimes it's going to look like an upside down U. We've talked about the fact that salt just means an ionic compound. So since an ionic compound is made up of a positive and negative ion, you will see ions going back and forth through the salt bridge. That's also something that appears a lot on the Regents. You have what the purpose of the salt bridge is to allow ions to flow back and forth. The ions help keep the solutions neutral. So ions go through the salt bridge, which makes sense because the salt is an ionic compound. Electrons go through the wire from the anode to the cathode. You identify the anode as being the one higher on table J and the cathode being the one lower on table J. Alright, so since electrons are leaving the anode and going to the cathode, meaning leaving zinc, over time the size of the anode is going to get smaller because it's losing electrons, it's losing mass. Over time, the cathode will get bigger because it's gaining mass or gaining electrons. What's happening really in terms of oxidation and reduction is that zinc is losing electrons and forming zinc ions in solution. Copper ions in solution, because copper sulfate is +2, are being reduced and become copper solid. When you're reduced, if you're looking at like the charge of the ion is typically going to be aqueous, and when you're a solid or you're being reduced, you'll see it in a solid form. We'll show you that in a few minutes. We also need to know the charges of our anode and cathode. The anode is negative. Remember, anode has an N in it. So for this voltaic cell, the anode is negative, and the cathode has a plus sign in it. It's positive. So sometimes they'll ask you, like, what's the charge of the anode? What's the charge of the cathode? And we need to know that ions will move in a direction to keep the anode negative and to keep the cathode positive. So that will be something that we'll be seeing as well. So that negative ions will move towards the anode to keep the anode negative, and positive ions will move towards the cathode to keep that cathode positive. So we'll take it one step further and we'll be able to write half reactions with voltaic cells. We know that the anode is zinc because zinc is higher up on table J. That's the one that's oxidized. So keep in mind, if I'm asking you to write a half oxidation reaction, I could look at the charge of zinc in the solution. Sulfate is -2. Zinc is going to be +2. If it's oxidized or losing electrons, it's becoming more positive. So zinc goes from 0 to +2, and we'll put our electrons on the right because we're being oxidized. So they could ask you to write a half reaction for the reaction happening in, if we want to call this half cell 1, or they could say write the half reaction that's happening in half cell 2, or we could just say write the reduction half reaction occurring in the reaction. Copper is going from +2 to copper solid. Since it's becoming a solid, it's going to have an oxidation state of 0. So the ions in solution gain electrons, attach to the electrode and become solid, where they'll have a 0 oxidation state. Since copper is being reduced or gaining electrons, we're going to show the electrons on the left-hand side of the arrow. And that'll be something that we'll be doing moving forward. We'll do some practice tomorrow where we'll write half oxidation and reduction reactions for a particular reaction, looking at half cell 1 or half cell 2. Sometimes the question will just say, what's the half reaction happening in half cell 1 or half reaction happening in half cell 2? Or they could say, write the oxidation half reaction, which will refer to the reaction happening at the anode, or write the reduction half reaction, that happening at the cathode. So for now, what I'd like you to understand about the voltaic cell is a couple of things. One, how to identify the anode and cathode, the anode being higher up on table J, the cathode being lower. Know what's happening at the anode, so anox, anode is where oxidation is occurring, red cat, reduction at the cathode. We want to know that the size of the anode is getting smaller because it's losing electrons. The size of the cathode gets bigger. We need to know that electrons go through the wire or the external circuit, and that ions go through the salt bridge to keep the solutions neutral. And finally, we want to know that this is a spontaneous reaction, meaning that if I put these two metals in these solutions, the reaction will occur on its own. It's going to chemically have a reaction, chemical reaction, redox reaction, to electrical energy. So this produces electricity, and we could read the electricity value or the voltage value with a voltmeter, or see it by looking at a light bulb light up by attaching it to the circuit. So it's spontaneous, it goes on its own, converts chemical energy to electrical energy.